Today we'll take a look at what has to happen to make possible basic communication between the host and device. But before that, I'd like to discuss some theoretical topics so that the code I'll write later makes sense. First of all, in USB there are two types of transfer, namely in and out, meaning that the data goes inside and outside the host. It's interesting because if the device outputs the data, it is called an in transaction. The transactions are named relative to the host. Second, the device needs some kind of buffer on its side to keep the data that's about to be sent or the data that has arrived. It is done using FIFOs. The device has one receive or RX FIFO and one or more of transmit or TX FIFOs. The reason why there may be multiple TX FIFOs is that the device may have several types of data and the host may prioritize between them. Say for example we are creating a USB camera device. It can transmit video, it can also transmit sound. But if for some reason the host is unable to process both video and sound, it may decide to discard the video and only receive sound. On the technical side, it is implemented using something called endpoints. A good way to think about an endpoint is a buffer. Endpoint is a special buffer for a separate kind of data, but they have a special feature that makes them not exactly buffers. Every endpoint is assigned a type depending on what data and how much of data it handles. Depending on whether it is a lot of data like video or files, a little of data for a USB mouse only to transmit coordinates of a pointer. If occasional mistakes in the data are tolerable, an endpoint can be assigned one of four types: control, isochronous, interrupt, or bulk. Returning back to the camera example, we may configure the endpoint as follows. The sound will be transmitted by endpoint 1, which should be able to handle lots of data but occasional mistakes are acceptable. The video will be transmitted by endpoint 2, configured similarly, optimized for a large amount of data, and mistakes are tolerable. The host may then decide to fetch data only from the endpoint 1 if it doesn't want to handle video. From another side, the endpoint can be classified using their direction. In endpoints that transmit data to the host, and out endpoints that receive data. So overall, an endpoint can be configured using three values: direction, number, and type. Its direction is actually embedded into its number by setting the most significant bit to 1. So in endpoint 0 will have number 80 in hex. Next we take a look at the library that simplifies working with USB and STM microcontrollers. HAL, or Hardware Abstraction Layer, is a library used to drive most peripheral into microcontroller. It manipulates the registers, does error checking, and provides us, the users, a high-level API. It operates two ways. First, it handles a single USB-related interrupt, figures out what event has happened, and calls a callback provided by user. An example event may be that a message has been received or sent, or that the host requested some data. The second way is that it provides a high-level functions we can use, like to send a message or receive one, or to activate USB peripheral, etc. There are quite a few callbacks supported, but we only need 4 of them to make the basic communication possible. So let's take a look. The first callback, the reset, is issued when the device connects to the host. It means that all the buffers has to be cleared and the device must be prepared to send and receive messages. Second is the setup callback. It is fired when the host is requiring communication. Then, if the host has requested an in-data transfer and the device transmits the data, and if the transmission was successful, the third callback is fired, called data in. Afterwards, the host must confirm the receival of the message by sending an empty packet. When this packet is received by the device, it fires fourth and final callback called data out. Aside the functions and callbacks, the HL provides a data structure representing the USB peripheral. It is called a handle. It stores lower-level details like registers locations and their values, which may or may not be useful for us, but HAL needs this structure for every operation it performs to know exactly what peripheral it is applied to. The library creates and initializes the handle itself, so we will just take it and pass to every USB-related function. This is it about the theoretical part, and now let's go write some code. In our main file, we have a USB initialization function right here, and there is a USB handle here, which is defined under drivers HAL HLPCD.c. Here it is. This file has a bunch of functions like reset callback here, data in, data out, etc. This we keyword here means that we can override this function. Here we have the setup stage callback, the one that describes a request, the data in stage and data out stage callbacks. Somewhere down here we have the setAddress function, which we will call when the host assigns us an address, the functions that open and flush or clear the endpoint. We also have one more file that contains 5 related functions. We will start our code by initializing the transmit FIFO, so I'm copying this function, paste it in my code, and now I have to provide the right parameters. The handle will be this one, the FIFO number. Well, I take a little thought about it, but eventually settle on 0. And the size is 512 bytes or 200 in hex. Now we need to configure the receive FIFO using a similar function from the same file. Moving it to the main file, the handle is the same. It does not take index because there may be only one RX FIFO, and the size is 512 bytes. And now we're able to activate the USB peripheral. To do that, we need to call another function from the HEL driver called PCD start. Here I use search to find it, and finally copy it into my code. Now, the rest of the code I'm willing to keep in a separate file, so I will create one. Call it myusb.c and include stdio header because I'm planning to use printf here. I'll clean up a space a little and start by implementing the reset callback as it will be called first. I will move the function into my code, and all it's gonna do is to print that it's executing. Now my handle type is defined in the HAL header, so I copy-paste the include here. Check that the project builds without issues and launch debugging. When I open the data console, I see the initial hello message but nothing from the reset handler. Well, there is clearly a problem here, and I think the USB interrupt is not fired. I open the interrupt file, search for the right function, and it is not there. In the C file, it is also absent, and the thing is that CubeMX does not enable the interrupt by default. So I'm launching it again to fix the problem. Under Connectivity USB OTG section, there is a checkbox to enable the interrupt. I regenerate the code after checking this option. Verifying that my code stayed in place, it really could disappear, and verifying that the correct interrupt function did appear. Running the debug again to see what happens. I see the hello message. Now I'm gonna insert my device, and there is a message from the reset interrupt, so it's working. Alright, let's think what needs to happen at the reset event. Well, endpoint 0 has to be activated, but before enabling the endpoint we have to make sure that it does not contain any outdated information, so we call flush function first. The function takes the USB handle, and I decided to take the global one from the main file, while there is one right there in the arguments. My bad. Anyway, we have to set the endpoint number, it will be 0. The endpoint open function has to know the maximum packet size, it will be 64. Okay, that was for the out endpoint 0. We have to do the same for the in endpoint. The difference in the endpoint address. In endpoint address is going to store 1 in the most significant bit, so in endpoint 0 is 80 in hex. That looks good. Let's see what other callbacks we have. These two are fired when the receival and transmission of data is complete. I'll copy them too. And only one more callback we need for now, the one for setup stage. In the implementation, I will first write a message, then list actual data received. There is always 8 bytes in the setup packet. The data is stored inside the handle, a field called setup. I will print every byte from it. In the data stage, I will only write a message so that we know that the event has happened. That looks good, let's run it. Well, I did not define the global handle I'm using for the reset callback totally unnecessarily. I have to define it. Now give it another build, and this time it looks better. Alright, I see the callback is running, but there is no actual data printed. The thing is, the line is printed in the console only when the new line character is met, so I have to add one. Run it again, and this time I see some data printed to the console. The setup packet runs again and again because the host expects a response which we don't send, so we should send response. I'll write here the data that the host expects. It's something called device descriptor, a data that describes the device. We'll look closer to it in the following video. For now, it's just a set of magic numbers. Now we have to send this data in response to the setup packet we receive. The function that does it takes the USB handle, pointer to the data, and length of the data. That's almost it. Let's see what happens if we run this. We got a new message signaling that data in stage has been completed. The process does not go forward though, and we receive the same setup packet again. The problem is that when the hosts have received the data, it sends one more empty packet which we have to explicitly receive. So here I'm calling for receival of zero length packet and run it again and see a couple of things. First, both data in and data out stages were completed. That means that the data was sent and the status packet has been received. And second, we now have another setup packet coming, starting at 0, 5, opposed to 80, then 6 as before. Now, since it looks like the device does exchange data with the host, let's see what it looks like at the host side. I'm loading the USB monitor module and starting Wireshark. Selecting the USB mon from the list and setting the device address as 0 since it is the address of newly attached device. And when I attach my device, I see a couple of messages appear on the screen, the request for device descriptor and the response to it. If I click on the setup data here, I see exact same information that was printed in my console, 80, then 6, 0, and so on. I can also see the raw request data down here. Next, we may explore the response to make sure that the data was transferred correctly.